Let's go ahead and start chapter 6, normal curves and sampling distributions. Graphs of normal curves, normal probability distributions. So just so you know, when you hear of normal probability distributions, in theory, your courses, your college courses should always, your courses should always have a normal distribution, which means you should have some amount of F's, a little bit more D's, the majority C's, and then the B's should kind of match the D's, and then the A's should match the F's. That's a true normal curve. My students always break the curve, so it just kind of happens. Go ahead and take a look at your focus points. And just a reminder that my YouTube videos are on the canvas under the home screen. You do not need a passcode. They are not related to Zoom. I convert them for you so you can look at them at any point in time. Okay. Focus points. We're going to graph a normal curve and summarize its important properties, apply the empirical rule to solve real world problems, and use control limits to construct control charts, examine the chart for 3 possible out of control signals. Remember, you guys can always work ahead. And if you need to, just email me if you need me to reopen something, but you can always work ahead. All right, graphs of normal probability distributions. One of the most important examples of a continuous probability distribution is the normal distribution. This distribution was again studied by another French mathematician, Abraham de Moivre, sure, and later by German mathematician Gauss, whose work is also very important, and it's sometimes really called the Gaussian method. Okay, the work of these mathematicians proved to be foundational, which is why the majority of the theory is based on them. Okay. Mean and standard deviation of the population is still being used. I don't know why they brought in the Boy Scouts. It is only through this formula that we can verify if a distribution is normal. However, we can look at a graph of a normal distribution and get a good pictorial idea and some of the essential features of a normal distribution. So remember how I told you guys, like I kind of broke it up for you, like the F's would equal the amount of A's, the D's equal the amount of B's, and then the C's are kind of in the middle. That is normal, and we tend to call it a bell curve because it kind of goes up and then right back down, looking like you know, kind of like the Liberty Bell. Okay, so here it is drawn out for you. If you take a look down at the bottom, you have your mean in the middle, which is basically going to be your middle grade point there. You have mean minus 1 standard deviation and to the left and plus to the right. And then it just keeps going. Let's see. These inflection points, you're really not going to be able to tell what they are unless the graph is kind of specific because it is a normal bell curve. Okay. All right. We see the general normal curve is smooth and symmetrical about the vertical line extending upward through the mean. Notice that the highest point on the curve occurs over mu. If the distribution were graphed on a piece of sheet metal, cut out and placed on a knife edge, the balance point would be the mu. We also see the curve tends to level out and approach the horizontal x-axis like a glider marking a landing. That just means that's just the lower part. So Theoretically, though, that glider will never reach the x-axis because it is a normal curve. The parameter sigma controls the spread of the curve. So basically, the most you'll ever see will be mu plus 3 sigma and mu minus 3 sigma. So you can see there that sigma is really important with figuring out your curve. Okay, which I believe I already mentioned that. So there it is again. Okay. Yeah, we're not going to continue talking about this ridiculously. It's literally all the same. Okay. Here's your properties, and you definitely want to write those out because you will have to know them for the exam. So the curve is bell-shaped and the highest point is over the mean. The curve is symmetrical about the vertical line through the mean, and the curve approaches the horizontal axis but never touches or crosses it. The inflection or transition points between cupping upward and downward occur above mu plus sigma and mu minus sigma, and the area under the entire curve is equal to 1, right? I could see those being multiple choice. I could see those also being true or false, although, yes. If you haven't noticed, I've done you all a favor. At least I believe it is favor. True and false was always something that I would get wrong more often than I would get it correct. So I literally did not give you guys a single true and false question. And if I did, then it slipped through the cracks. I'm obviously not going to change the exam at this point, so I guess you might have one or two that may have slipped in, but the majority of true and false should not be on your exams because I detest them. Regardless, make sure that you have this written down. Whether you take a screenshot, come back to it later, or you write it down now. It is very important. Okay. All right. Empirical rule. For a distribution that is symmetrical and bell-shaped in particular, so basically the normal distribution, approximately 68% of the values will lie within the first standard deviation, 95% will lie within the second, and 99.7% or the vast majority will lie within 3. The next thing should break that down for you, and it does. You want to draw this out or write it out or chart it out, whatever is the best for you. This is ridiculously hit on. If it's not going to be on your exam, it's definitely going to be in your homework. I assume it'll be on your exam. This will be one of the things that when you leave this class, the majority of anyone else, any other class that you have that's related to statistics, they will expect you to know this rule. Okay, it's one of your major cornerstones in statistics. So go ahead and write that out. Make sure you ask me if you have any questions on it because I will answer it. And some of the questions related to this empirical rule can get tricky. So make sure you read your questions closely. And also remember that if you need extra attempts on homework or quizzes, just email me and I will increase the number of attempts. Someone let me know with a thumbs up or a chat message when you're good to go with that. Okay. All right. Notice that the empirical rule is a stronger statement than Chevyshev's theorem in that it gives definite percentages, not just lower limits. A Chebyshev, if we haven't already covered that, then it's coming. It's another big cornerstone. But again, you can see that this is very, very succinct. Okay, you can't really mess this up. If you do, then it's just you writing it wrong, not really anything else. All right. Of course, the empirical rule applies only to normal or symmetrical bell curved distributions, whereas Chevyshev's theorem applies to all distributions. Okay. All right. So let's look at an example. The playing life of a sunshine radio is normally distributed with a mean of 600 hours and a standard deviation of 100 hours. What is the probability that the radio selected at random will last from 6 to 700 hours? So basically, you should be able, if you're given a mean and the standard deviation, you should be able to draw out your normal bell curve. Once you draw out your normal bell curve, you should then be able to draw in your empirical rule. Since mu equals 600 and mu plus sigma equals 700, we see that the shaded area is simply the area between mu and mu plus sigma. So the area from mu to mu plus sigma is 34% of the total area. So then that tells us that the probability of sunshine radio will last between 600 and 700 playing hours is about 0.34. Okay. Any questions on how they got that? No? Good. All right. Control charts. If we are examining data over a period of equally spaced time intervals or in some sequential order, then control charts are especially useful. Business managers and people in charge of production processes are aware that there exists an inherent amount of variability in any sequential set of data. The sugar content of bottled drinks taken sequentially off a production line, the extent of clerical errors in a banking from day to day, advertising expenses from month to month, or even the number of new customers from year to year are examples of sequential data. Okay, there is a certain amount of variability in each. A random variable X is said to be in statistical control if it can be described, but the same probability distribution when it is observed as at successive points in time. Control charts combine graphic and numerical descriptions of data with probability distributions. Oh boy. So control charts were invented in the 1920s by Walter Shewhart at the Bell Telephone Laboratories. Since a control chart is a warning device, it is not absolutely necessary that our assumptions and probability calculations be precisely correct. For example, the X distributions need not follow a normal distribution exactly. Any mound shape or more or less symmetrical distribution would be good enough. All right, go ahead and write out your procedure. Okay, so the first thing you want to do is find the mean. The second thing you want to do is find your standard deviation. And that's as long as they're not given to you. So for part A, it says using past data from a period during which the process was in control or using a specified target values of mu and sigma. Create a graph in which the vertical axis represents the X values and the horizontal axis represents time. Draw a horizontal line at the height of mu and horizontal dashed control limits at mu plus or minus 2 sigma and mu plus or minus 3 sigma. Plot the variable x on the graph in time sequence order. Use line segments to connect the points in time sequence order. Okay. Pretty big procedure there. In a minute, we're going to look at an example, I'm sure. So here's your basic example. I'm not going to go through and read it. I just want you to have an idea of how to manipulate this data. So there's a table here, make a control chart for these data. Right, and then, you know, there was a whole bunch of information, so that helps you gather this up. Then you have to figure out your mu plus 2 sigma and your mu plus or minus 3 sigma. And there you have your control chart diagram. I do not recall students having issues with this last time I taught it. So either we skipped the section or they didn't have any problems with it. So, but we couldn't have skipped everything. So no, I just don't think they had any problems with it. All right. Okay. So this is kind of cool. 3 of the most popular warning signals that exist in this control setting. You have out of control signals, which you can see that here. Out of control 2 and out of control 3. So I'm going to take a quick screenshot if I can of that. Cool. I think I got the full page. So if you guys need that a little bit more zoomed in, I can send you that screenshot. I'm sure it's also in your textbook, so you can also look at it there. We are again in 6.1. All right. I'm not going to go through and discuss any of this, but make sure you read it on your own. You may have homework questions regarding it. Okay. Remember that a control chart is only a warning device and it is possible to get a false alarm. So you basically want to use this to help you. And if you were in a job where you would use it, you would not, you know, go around screaming wolf all the time. All right. Here's your probabilities that you could have a false alarm depending upon the warning signal type. From an intuitive point of view, signal 1 can be thought of as a blow up or something dramatically out of control. Signal 2 can be thought of as a slow drift out of control, and signal 3 is somewhere between a blow up and a slow drift. All right. Any questions on 6.1? No? You guys should definitely be able to do the homework on all of chapter 5 and as well as now 6.1. We will see how far we get with 6.2. Looks like we should be able to cover the whole thing, which is great. And then you should have all of spring break to study chapter 6 and 5 after next week. Okay. All right. Standard units and areas under the standard normal distribution. So, given a mean and a sigma, convert raw data to z-scores. Given a mean and a sigma, convert z-scores to raw data. given the standard normal distribution and find areas under the standard normal curve. Okay. Z-scores and raw scores. Once we start with Z-scores, you probably will not stop seeing them. Okay. And if you can print out your Z-score table, I highly recommend doing so. Normal distributions vary from one another in two ways. The mean may be located anywhere on the x-axis, and the bell shape may be more or less spread according to the size of the standard deviation. The differences among the normal distributions cause difficulties when we try to compute the area under the curve in a specified interval of x values, and hence the probability that a measurement will fall into that interval. That's why the z-scores exist. It would be a futile task to try to come up with a table of areas under a normal curve for each mu and sigma combination. We need a way to standardize the distributions so that we can use one table of areas for all normal distributions. We achieve this standardization by considering how many standard deviations a measurement lies from the mean. In this way, we can compare a value in one normal distribution with a value in another different normal distribution. The next situation shows how this is done. Okay, so this is like a scenario that we're going to use, but it will end up helping you kind of understand z-scores a little bit better. Suppose Tina and Jack are in two different sections of the same course. Each section is quite large, and the scores on the midterm exams for each section follow a normal distribution. In Tina's section, the average mean was 64, and her score was a 74. In Jack's section, the mean was 72, and his score was an 82. Both Tina and Jack were pleased with their scores. Both Tina and Jack were pleased that their scores were each 10 points above the average of their respective section. However, the fact that each was 10 points above average does not really tell us how well they did with respect to other students in that section. Figure 614 shows us the normal distribution for grades for each section. So this is Jack's section. The mean was a 72 and his score was an 82. Tina's 74 was higher than most of the other scores in her section, while Jack's 82 is only an upper middle score in his section. Tina's score is far better with respect to her class than Jack's score is with respect to his. The preceding situation demonstrates that it is not sufficient to know the difference between a measurement and the mean of the distribution. We also need to consider the spread of the curve or the standard deviation. What we really want to know is the number of standard deviations between a measurement and the mean. This distance takes both the mean and the sigma into account. Okay, so basically, this is how you find a z-score. So you really want to write this down. In words, the number of standard deviations between the measurement of the mean is equal to the difference between the measurement and the mean divided by the standard deviation. So in mathematical statistical symbols, we say that the z-score or z-value is equal to x minus mean over sigma. Okay, so x minus mu over sigma, or the x value minus the mean divided by the standard deviation. Go ahead and write down how you find the z-score. You will not ever forget it because you will use it so many times in this class. Right. Mean is a special case when it comes to this distribution. So if you are looking at x equal to the mean, then you have a z-score of 0, which I believe gives us 50-50. I think so. We'll have to take a look. So here, if x is equal to mu, we have a z of 0. If x is greater than mu, then we'll have z greater than 0. And if x is less than mu, we will have z less than 0. You don't really need to know that because you will end up figuring it out on your own after doing so many of these problems. A pizza parlor franchise specifies that the average amount of cheese on a large pizza should be 8 ounces and a standard deviation of only 0.5 ounce. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it is made with a 6.9 ounces of cheese sauce. Assume that the amount of cheese on the pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. Dun, dun, dun. How many standard deviations from the mean is 6.9? Is the pizza parlor in danger of losing its franchise? Since we want to know the number of standard deviations away from the mean, we want to convert 6.9 to standard z units. So we're going to take x, which is our 6.9, minus our mu, which I believe was 9, divided by our 0.5. Well, 8. So then our z-score there is negative 2.20. Now that we have that, we have to find our probability. So now you would go into the z-score table. Oh. Given an x distribution and a mean and standard deviation, the raw x score x corresponds to a z-score. X is equal to, they just rearranged it. Z times sigma plus mean will give you back to your x. If you looked at the original equation, you could solve that yourself using your algebra. All right, standard normal distribution. We are nearly done, so just hang tight. We're going to finish this, and then I'll let you go. We're going to do it fast style. All right. The standard normal distribution is a normal distribution with mean equal to 0 and standard deviation equal to 1. So areas under the standard curve, now this is where the z-score comes into play. So the rule that we just learned will help you out as long as it's a standard normal distribution. However, if you have to use z-scores, you have to use the standard normal distribution table. Let me just get you to it so we can look at an example. All right, so remember before how the answer was negative 2.20 as your z? You would come into your z table, you would drop down to negative 2.20, and you would look over to find that. Let's take a look real quick as to what they want us looking at here. Find the area under this normal curve to the left of z equal to negative 1. Here's negative 1. Here's your negative 1. Here's your 0, 0. So you're looking at an area of 0.1587, which would give you a probability of 15.87. All right. If z is equal to 1.18, we look at the table. 1.1.08 gives us 1.18. So 0.8810, which is a probability of 88.10. Any questions on how to use that table? All right, here's your procedure. For the area to the left of a specified z value, use the table entry directly. For the areas to the right, you have to look it up and then subtract that area from 1. There is If you choose, you can Google it. There are z-scores that are negative and positive. You can look just for the positive z-score table. You can look for the negative z-score table. You can look for one that has both. Again, I recommend printing them out. All right. Here's your convention. Treat any area to the left of z smaller than negative 3.49 as zeros, and treat anything to the left of z greater than 3.49 as a 1. You can choose to do that. Some of the tables may have something different. I don't think that we need to keep going with the examples, but for the sake of the video, I will go through all the slides and then you can pause them later to go through more examples if you feel like you missed something or would like to see more examples on your own. All right, that is the end of 6.2.